Hello, Internet. Let's talk about software and efficiency because one of the things that has happened is that software has gotten incredibly slow. If we look at the old days, like if you go back to the 1970s, computers, hardware, CPUs, central processing units, were so slow that the programmers at the time needed to be very, very good at efficiently using every cycle, right? And as a result, programs were typically very well written, but at the same time, it took a long time to write them. But over time, the CPUs have gotten faster, and we've gotten better and better co-processors, GPUs, and so on. But alongside that, there's been an attitude change to essentially companies and people, software developers and everything like that, being okay with just wasting CPU time, wasting cycles, just being wasteful. And the argument that they make is that programmers are expensive, but we can always just buy more computer, right? Except when you take that attitude and multiply it over all software in the world for decades on end, then you're eventually going to come to a situation where the software just eats up all of the progress that's being made in the hardware, and then some. And so we see today software is typically running somewhere between 500 and 1,000 times slower than it could be running, right? And a lot of that's there's a lot of different reasons why that's happening. One part is just the programmers choosing bad algorithms, doing things in bad ways. Part of it is layers upon layers of abstraction, right? If you add enough different abstraction layers, you're going to end up with the statements that you're making on a high level being so removed from what's actually happening on the hardware that there's multiple layers of indirection and translation going on in between, and that's going to accumulate slowness. In one extreme example, a few years ago, there was somebody who took a look at the Google Chrome codebase and discovered that when you typed in a single character into the input box, where you put the URL, or what you want to search for, there would be tens of thousands of memory allocations that would happen just from a single letter. And the reason was that Chrome is written in C++, and C++ doesn't have a standard method of storing text strings, right? So there is something called std string, and then they also have a char pointer or a character pointer, and there's a few other ways to do it. And then Boost has its own version, and different libraries have their own version of strings. And so what happens is you end up with thousands upon thousands of conversions between different string types, because different libraries want to store things in different ways. And so just something that came from a fairly honest, simple mistake of just not having a standard string format, multiplied over a couple of decades, 3 or 4 decades, and then multiplied over a very large code base, and you end up with a situation where there are tens of thousands of memory allocations happening every time you press a button. And obviously that's going to eat into the speed at which your programs run, right? And then on top of that, you have this other thing where, so in the old days, CPUs and memory used to run at similar clock speeds, and the communication between the CPU and the memory used to be roughly 1-to-1. So in one clock cycle you could read a reasonable amount of memory from RAM, right? But over time, CPUs have gotten a lot faster, but memory has stayed roughly, like, it's gotten faster too, but it hasn't gotten faster as fast, right? So as a result, you have a situation where it's gotten more and more difficult to get data from memory, where it's taken more and more time, rather. And as a result, CPU developers responded to that by creating what's known as a cache hierarchy. And it comes in sometime in the late 90s, right? So nowadays, what happens is the CPU speculates about what data it needs to fetch, goes and sets that fetch in motion while it's doing all sorts of other computation. And with any luck, by the time the data is actually needed, it will already have arrived in the cache, right? And so it's a lot faster to get at. Now, I'm simplifying here, but that's one of the mechanisms. The other is that the data, if it's frequently used, it's going to be in the cache anyway, things like that, right? But in the event of data not being in the cache when you need it, you essentially have to wait. And that can be up to 200 cycles, like, give or take. It varies from CPU to CPU, it varies on a number of factors, but 200 cycles is not unusual. And that's a situation that we call a stall, right? Now, some data structures that every programmer in the world has been taught to use are such that they are more likely to yield kind of stall situations than others, right? So one that programmers were always taught in the 90s is something called the linked list. It's a very basic thing. It's a list of items where each item contains a pointer to the next item, right? So it becomes a bit of like a chain. In the 90s, this made a lot of sense because RAM was expensive, there wasn't a lot of it, and so the likelihood of you finding a gap in memory, or like that you could stick another list item into, was like, depending on the size of the item, this could be quite tricky. Whereas nowadays the script has flipped. There's, computers have gigabytes of RAM. It's not a problem most of the time to find gaps, but it's become very costly to seek randomly into the memory, especially if there's no way for the CPU to predict which bit of memory you want to fetch. And so something like this simple format of a linked list used to be the way to do things, and it was taught as such, but now it's become a liability. Now it's become the way that you absolutely do not want to do things ever. And yet, it's not that linked lists are the only culprit here. There are many data structures that have similar characteristics. And of course, there are ways to use clever allocation methods and whatnot to speed up linked lists. But there's a change in the methodology that you need to use that a lot of the people in the software industry haven't adopted because they're still being taught the old methods. And on top of that, you have this attitude that it doesn't actually matter if things are slow. So let's put this into context a little bit. Slowness of software is eating up enormous amounts of CPU time. It's making your laptop, your brand new laptop, seem sluggish when it's got a couple hundred tabs open, right? Or even like relatively small workloads, things can seem sluggish. Your new phone might seem sluggish for all sorts of reasons. Like, all of the software just seems slow. And if we look at what exactly is causing that, like, it's just accumulated little inefficiencies multiplied over decades of software development. Now, CPUs, of course, in the process of doing all this stuff, not only are new CPUs costing money, they're also spending energy. And that energy is it needs to be generated somewhere, so there's an energy generation cost associated with it. There's also a carbon dioxide cost and other emissions costs associated with it. Depending on where you live, that could be quite a lot. So the benefit of reducing the amount of energy your CPU needs to use by, say, half can be quite substantial. Maybe not for one device, but imagine a program that runs on every device, or a program that runs on quite a lot of devices. If you could convince that program to run twice as fast by changing some underlying algorithms, or by improving the data access speed, or reducing the number of CPU stalls, or any of these things, right? And it's not just the things I've mentioned, it's also a bunch of other stuff. Like I'm simplifying, I'm generalizing, but if you could get some piece of software to run twice as fast, then what you achieve by doing that is maybe a net reduction in energy use by quite a significant factor, right? And honestly, I think that the software industry has a bit of an obligation to try to do that, to go and fetch that, both because it makes the lives of our users better, because the software just seems faster and is faster, but also because it's good for the planet. And on top of that, there's this other benefit that I think programmers need to think about, which is there's this magical beauty that comes from removing all of the unnecessary cruft. The satisfaction that you can only really get by making things faster, by deleting all of the stuff you don't need. It feels magical. It's so much fun, and I can't recommend it enough. So yeah, I think we as a software industry need to really start thinking about the efficiency of our code. I think parts of that will be to try to move closer to the hardware. Part of it's learn better about how the hardware works. But the number one thing is to get rid of this stupid, entitled attitude when it comes to software development, that the speed of your code doesn't matter. It does, and if you think it doesn't, you're wrong.